Hello, good morning, good afternoon, and good evening, everybody. My name is Gerald Pasquale, and I'm with Technical Marketing here at Park Systems. We are a leading manufacturer of atomic force microscopy and emerging nanoscale microscopy technologies and solutions. And today, we are continuing our 101 series with Professor Rigoberto Advincula of Case Western Reserve University. We have Polymers and Plastics 101. It's an overview and a review of this field. So if you are new to this particular series, you'll notice that you have joined the session in listen-only mode, and that's by design. We'd like to give our speakers an uninterrupted platform to convey the material that they wish to share with you guys. But we also want to encourage you guys to send in your questions in real time using the questions, the chat module that has appeared in your control panel when you joined in the session. So anytime you have a query, go ahead and punch it into us, type it in, and what we'll do is at the end of Professor Advincula's talk, we will address those questions sequentially. That being said, we will also have this session uploaded to the Park Systems YouTube channel, but I'll go ahead and review that with you guys right before we start the Q&A later on. So without further ado, let me turn things on over to our guest speaker, Professor Advincula.
Okay, well, thank you very much, Gerald, and good morning, good afternoon, and good evening to you all. As Gerald mentioned, this is a continuation of a series we've been holding called 101 series. If you're not able to capture this live, this will be shown in YouTube and at the Park AFM Systems website as well. I'm very excited about this particular webinar because this is dear to me as a polymer chemist, but I'd also like this to be useful to every one of you who would like to have a 45-minute, 1-hour vignette or a series of vignettes about what the polymer and plastics field is. And then at the end of this webinar, I will be happy to show you the latest things coming from our lab. So to begin with, I'm with Case Western Reserve University in Cleveland, Ohio, and we are part of the Case School of Engineering, and I'm with the Department of Macromolecular Science and Engineering. If you're in town to visit the museum, lake, or even attend an orchestra, just let me know, and I'll be happy to accommodate your visit. We have a long history dating back to 1826. Several Nobel Prize winners have been part of our faculty, student body, or once students here, including Henry Da, who's an alumnus of our university. So we're located at the Macromolecular Science Engineering building. I'm at the 5th floor, and our labs are at the 3rd and the 1st floor. We do a lot of work related to interfaces, macromolecular reactions, layer by layer structuring, nanopatterning, and I will not have an opportunity yet to discuss most of this latest stuff with you, but hopefully at the end I will give you some indication of where we have taken polymer science to new heights. On the other hand, I want to emphasize and let you know that working with industry is a very important task in our group, in that we want to be relevant, we want to solve problems, we want to help different innovation, problem solving, and other company platforms, not only for the interest of the company, but also the training of and work of my students related to industry. So let's go on with the tutorial. What about plastic and polymers? What is the first thing that comes into your mind when you think about plastics? Are plastics and polymers the same? Is rubber considered a polymer or even called a plastic? And what are the terminologies, the concepts for polymerization, the processing, some of the properties of polymers in general that differentiate it from small molecules? So these are the type of questions I would like to help answer or even demystify within the next 45 minutes. So obviously here we have a collage of different plastic, polymer, packaging, rubber products that are available every day. So I would like to call polymer science as the chemistry of everyday things. Paint, packaging, there are many things in common between paint and rubber. That is, you blend and add additives to give them the consistency, the rheology, or the impact strength that makes them useful for society. However, we can take a look at these large molecules in a different scale. These polymers are, after all, large molecules. And large molecules means we can stretch them, we can make them compact, depending on the solvent, depending on the surface. They can adsorb, they can order, they can phase separate, or they can even form complexes that are related in scale to colloids and nanoparticles. In fact, I like to look at polymers as true nanomaterials, or sometimes they refer to them as soft matter, in that we can do manipulation together, let's say with quantum dots, graphene, or carbon nanotubes in a scale that they are compatibilized, or they interact as nanomaterial systems. Well, let's try to define some terms. Appropriately, the more popular word is plastic. Plastic comes from the Greek word called plastikos, or to be able to mold or shape. What we are actually referring to are large molecules called polymers, or sometimes called macromolecules, that behave differently from small molecules. Thus, plastics are derived from the action, the property of large molecules called polymers. In fact, polymers are everywhere, including the human body. And around you, many things can be classified as polymers and not necessarily plastics. In the dimensionality of matter, you can see here that small molecules can be classified within the regime of elements or behavior of matter as liquid, solid, or gas. When these molecules are formed as compounds, they change in size and complexity. And as you can see in this plot, most polymers are in the order of 1 to nanometer or more in size range, and they can be quite complex. In other words, the properties of macromolecules are unique because they are big and specifically ordered, sometimes to differentiate it from what we call crystalline material in small molecules or inorganic matter. So what is a polymer? A polymer, again, is made up of large molecules. That large molecules are polymerized or made up from monomers that are stitched together to form a polymer. Again, the Greek word mer means many and parts. So polymer means many parts. A monomer, therefore, is the basic ingredient for a polymer. A monomer is essentially a repeat unit or a small molecule that can be polymerized to form the large molecule, and this can undergo either initiation, propagation, or a series of step growth reaction. However, we have a separate term for an intermediate size molecule. It's called oligomer. Usually, we reserve the term oligomer to maintain 10 or less monomer units. You may have heard of ethane, butane, propane, octane. These are oligomer units of methane or hydrocarbons. Polymerization, therefore, is the term that is used to synthesize these large molecules out of monomer units or simpler molecule monomer units. In fact, most common organic reactions can be utilized to make large polymers or complex coordination or complexation reactions. But it is safe to say that a good number of organic chemistry reactions can be turned into a polymerization reaction. So there is a minimum requirement for this. It's called functionality. There is a minimum requirement of functionality equal to 2 in order for polymerization to take place. So what is this functionality? A common monomer is called styrene. When you polymerize this monomer, you get polystyrene. And the functionality of 2 means these two carbons, which are pi orbitals with sp2 hybridization, is capable of reacting with a radical, an ion, or cation to produce polystyrene. Another example of that functionality equal to 2 is this amino acid. Alpha amino acid means the amine can react with the carboxylic acid, and in doing so, it can form a polypeptide or a polyamide based on the reaction of these two functional groups. Hence, we refer to a monomer as a molecule having a functionality of 2 that can propagate to form a polymer. Yet another simple example is the alkane series, or what we call methylene, or simply polymethylene, meaning a hydrocarbon like methane, ethane, propane will give you a gas, a liquid, and then larger molecules will give you a wax, and then even larger molecules will simply give you a solid polymer. And polymethylene is not easily prepared, but an equivalent or analogous molecule is polyethylene. In organic chemistry, we call this a homologous series of a molecule with increasing number of units. Or we simply refer to them as polymers or oligomers, made up of n number of repeat units of the monomer. Now, we will learn, or in briefly, we're going to see that a polymer is not as simple as synthesizing the molecule. The composition can be made by one component, or it can be made by two or more components, which we call a blend or a copolymer. And very importantly, we look at the molecular weight distribution, or the stereochemistry in order to characterize its structure property relationship. A very important task is, of course, analytical methods to characterize the polymer. And this can be done in solution or by microscopy and spectroscopic methods. Yet another way to characterize their polymer properties is by looking at their thermomechanical properties, optical properties, conductivity, and so on. And then lastly, these polymers, in order to make them useful, has to be processed. Therefore, processing can involve extrusion, molding, film formation, and it's very much dependent on the composition and additives that you put in to give the final product. Thus, we can say polymer science is made up of 4 pillars: properties, composition, molecular characterization, and processing. In fact, in our lab, we use atomic force microscopy a lot in order to characterize the morphology of polymer films using AFM. So let's define some terms for those of you who are yet familiar with some of these other properties. So a repeat unit, again, is a small molecule or a base unit that is polymerized to form a large molecule. A telecalic polymer or even oligomer is a small or a smaller molecular weight. The term telecalic is reserved for oligomers or polymers capable of further reaction. A polymer backbone is essentially the main chain of the polymer, okay, or main chain of a linear polymer. Together with dependent side groups, they can define the useful properties of a polymer. And then the term degree of polymerization is the number of n units that you multiply the molecular weight of the monomer to produce the polymer molecular weight. So degree of polymerization can be obtained essentially to get the actual molecular weight of the main chain. And then the term polydispersity is used to differentiate the distribution of chain lengths of a polymer. And this can be quite important because it can determine properties like glass transition temperature, rheology, viscoelasticity, and so on. We reserve the term polymer blend, referring to a mixture of two or more polymers or a polymer and an additive. The polymer blend can be miscible or immiscible. So, going to the constitution of a polymer can be made up of one type of monomer unit. We call this a homopolymer. Examples are shown here. Polystyrene. So polystyrene has one monomer base unit. It's called styrene. Polymerizing gives a homopolymer polystyrene. The same can be said of ethylene. Ethylene can be polymerized to produce polyethylene. Now, homopolymers can also refer to a different type of constitution. A copolymer is essentially a composition made up of two or more base units, or a covalent mixture as opposed to simple mixing, meaning these monomers are connected to form a new polymer. So two or more polymers can alternate between A and B, or it can have a random distribution. It can form a block of A and B, or a graph of A to a backbone of B, or it can form multi-blocks. This has to be synthesized and connected covalently in order to call them a copolymer versus that of simple mixtures. And this is how they look like. So different copolymers are important because they impart unique properties that cannot be accessed by simple mixing or blending. Some of the uses of these copolymers are for compatibilization, production of what we call thermoplastic elastomers, different types of viscosity modifying agents, or simply combining two or more properties that give you what we call a synergistic property or relationship. Now, polymers can be classified by chain architecture. So far we have focused on linear polymers. Random branch, meaning you have branching that is randomly introduced during polymerization. A good example is a low-density polyethylene. A design branch can be in the form of anionic polymerized initiators and macro initiators. And network refers to reactions involving cross-linking or interpenetrating networks. Cross-linking is in fact a very important differentiation from linear polymers because the cross-linking reaction requires a functionality of more than two. So in order to have cross-linking and network formation, you need to have a functionality of three or more, or you need to have a polymer which is capable of reacting with another polymer chain to form a gel and eventually a thermoset material. Uniquely, a polymer of two main chains that are connected to each other looks like a ladder. A polymer that assembles by itself or forced to assemble, just like proteins or other types of enzyme complexes, are supramolecular assemblies. Dendrimer is a form of branch polymer but are highly regular and topological. And then we call polymers that are hyperbranch, made up of polymers that have dendritic or fractal growth in branching. So this is a representation of the different polymer architectures that have been reported and investigated. Now, we don't have much time, but suffice it to say that the architecture, the linearity, the branching defines some of its useful properties. For example, linear polymers are capable, of course, of good crystallizability. Cross-linking results in gels or thermoset. Branching tends to lower the melting point and also cause a decrease in the viscoelastic behavior. Dendrimers, hyperbranch systems are interesting because they have high molecular weight but flow very well, or low viscosity. And of course, what's next? Okay. So again, for those of you who are new to polymers, how do we classify the polymerization process? Well, we can classify them to several terms. The use of the word addition polymerization means you have initiators that adds monomers and propagates to form a linear polymer. On the other hand, the old term condensation polymerization means that a polymer repeat unit reacts very early on to form oligomers that at the end of the reaction produces a high molecular weight polymer. These two are different from each other. In fact, condensation polymerization, the term simply means that there's a byproduct or a condensation product that is produced during polymerization. But some polymers do not produce a byproduct, but yet follows the mechanism of condensation polymerization. So a better term is based on the mechanism as defined by step growth or chain addition. So step growth polymerization means that the polymers are observed only at the end of the reaction, whereas at the beginning, a step growth of oligomers are formed starting from dimers, trimers, tetramers to go on and produce your polymer. This is actually how you produce polyurethane, epoxy, polyamide, silicones. On the other hand, the chain reaction, which can be substituted for addition polymerization as well, grows by initiation, propagation, and then termination. This is how you make polyethylene, polystyrene, polyvinyl chloride, and so on. A modification of this, of course, is that some polymers go via ring opening reactions or mediated by a coordination catalyst. That also can go through a chain or even a step growth reaction. Now, in summary, a chain growth reaction requires an initiation step, a propagation that produces the linear chain, let's say, and then a termination which halts or stops the polymerization. In a free radical reaction, this can occur by recombination or disproportionation, but some of the complications can come from chain transfer, either through the solvent, the chain transfer agent, or the polymer itself. Thus, as you can see in this plot, the polymerization proceeds with the formation of a high molecular weight at the beginning of the reaction, and then through the rate constant type, you can have a decaying rate, constant rate, or decaying to constant rate. In practice, the initiation can be done with a radical or actually proceeds either by cationic or anionic methods, or even by coordination reactions, or with the use of an organometallic or metallic catalyst. So in summary, you form a high molecular weight at the beginning. You still have monomers at the end of the reaction, and the active center can be in the form of an anion, cation, radical, or through coordination reactions. And the term living, as you find later, is reserved for a polymerization which have linear relationships on conversion, monomer initiator versus time, monomer concentration versus time, and also the ability to form black copolymers or macro initiators. Now, the second major type of mechanism is based on step growth. In step growth reactions, you have monomers that react early, and therefore all the monomers are consumed very early on to form dimers, trimers, and tetramers. You really do not see a high molecular weight at the beginning, but only the end of the reaction. In fact, a very important component or requirement is that the reaction should be a high yielding conversion or a high conversion reaction in organic chemistry, such as esterification, amidation, and so on. Very early on, they noticed this, or Carothers, which is a famous polymer scientist, characterized this as the relationship of the degree of polymerization with conversion given as 1 over 1 minus P. So what this simply means is that the higher the percent conversion, the higher the degree of polymerization, and therefore the molecular weight. So in order to get high molecular weight, that means P has to be of the order of 99%, 99.9%, or even higher to get high molecular weights. This type of polymerization is how you make nylons, esters, urethanes, carbonates, and so on. Okay. So let's classify polymers further. We can classify them as synthetic organic polymers. And most of the petroleum-based feedstocks ends up giving you synthetic organic polymers. Biopolymers can be derived from natural sources or isolated, such as cellulose, polypeptides, proteins. Semi-synthetic polymers could be modified biopolymers, so you can take cellulose and modify it. Inorganic polymers like siloxanes or silicones can be made or derived from inorganic components. And complexations of organometallic monomer units or complexations with ions results in organic metallic polymers. Now, polymers can be classified also by their chain configuration or stereochemistry or regiospecificity. This can be in the form of a head-to-tail, head-to-head, or tail-to-tail reaction or placement, such as observing addition polymerization, or it can be in the form of looking at the stereochemistry of the side or pendant group, either on one side, opposite side, or alternating. And this can be classified or observed here in the case of polypropylene, where you have a perfectly alternating or syndiotactic tacticity, or in the case of B, at the bottom, you have a random placement. Now, without much time, this can be observed by looking at the tacticity and characterizing, let's say, with a technique called NMR. Now, very important, a polymer can be classified as a plastic, or more accurately, a thermoplastic. Thermoplastic means you can use heat to change the shape or convert it into a viscous material. On the other hand, a thermoset is a term where we say that once a polymerization or cross-linking has taken place, you cannot change the shape anymore. The shape has been set. No matter how you heat, no matter how you try to change the shape, it will not. And these thermosets are very important because they provide some strength that cannot be easily obtained at higher temperatures. And therefore, you can use this polymer for other types of conversion processes. Now, the physical performance demands that a polymer can either be a rubber, a fiber, or even an adhesive. And this can be formulated together with the base ingredient polymer. The term resin is used to refer to a monomer or composition or formulation or even a polymer that has to be converted into another form. So resin is a very generic form or term for a polymer or polymer composition or blend. Now, some of you may be familiar with this graph. This refers to the relationship of stress versus strain. Different polymers, the way they are processed and the way they are cured or thermoset, or the distribution of crystalline or amorphous ingredient defines their thermomechanical behavior. So a toughened fiber, a brittle plastic, will show this stress-strain relationship. On the other hand, a elastomer can be stretched and stretched until it yields. And a typical plastic will show this behavior where you have the transition from a glassy to an elastomeric phase and finally the yield point, which can be represented by changes in the distribution and the amount of amorphous and crystalline species present on a polymer. So suffice it to say, most plastics are semi-crystalline. most plastics are semi-crystalline. That is, they have a crystalline and an amorphous component. So we can classify polymers by application. We can call a plastic, a fiber, a rubber, a coating adhesive, or we can classify a polymer based on crystalline content, highly semi-crystalline or even totally amorphous. So the term amorphous means that there's no particular order in any direction. Another term for amorphous is isotropic. Okay. Now let's talk about polymer blends. So sometimes a polymer only becomes useful if you add additives to enable you to process it or to give it color or to give it different reactivities. So blending two or more polymers or a polymer and an additive gives it a new property. It can either lower, increase the melting point, make it more soluble, or produce networks. So blending is a very important industrial process because this is what you do to process a product. Now, blending cannot be all the time useful. In fact, blending can give you a non-synergistic or opposite effect in that you get a negative property. On the other hand, blending can give you a synergistic effect, a good increase in the desirable property when you mix the two. And then, of course, you can blend two things and nothing happens. We call that additive blending. Now, when you blend, sometimes they mix together, sometimes they don't. If they mix and form a homogeneous phase, we call that a miscible blend. If they phase separate and without a compatibilizer, they are called immiscible blend, or it will result in phase separation or microphase separation. Thus, sometimes you need to add a compatibilizer to force mixing. Now, the control of this blending process is important because it can define, again, the thermomechanical properties. And between two polymers, you can have a range of compositions from 0 to 100%, and you can get a majority and minority phase. On the other hand, without blending, one can observe changes in properties by actually copolymerizing or using chemistry to link these units together. So copolymerization can be accessed through the various compositions as I showed you earlier, alternating, graph, or block. Block copolymers are important because they can form phase-separated systems that are in fact predictable. So in this so-called Milner diagram, you see these different types of morphologies or phases predictable by the composition and the volume ratio, and in fact the chi interaction parameter between these two components, giving you this very interesting phases or morphology. Now, block copolymer work is important, let's say, for production of rubber and thermoplastic elastomers. Now, there are other forms of polymers. Polymers can be in the form of gels. It can be in the form of foams. It can be in the form of nanocomposites. So, for example, aerogels means you have a high volume component of air, making it lightweight. A polymer can be mixed with nanomaterials to produce a nanocomposite that will give you high strength properties or very interesting diffusion control properties. Of course, a polymer can complex and form higher ordered hierarchical structures, or polymers that can be entangled in a very unique knot or manner, or even a virus can be classified as a polymerization of different proteins to produce icosahedral structures like this. So the term supramolecular assembly or macromolecular assembly can involve polymers that produce very important enzymes or functions or structural materials that can be isolated and observed by, let's say, TEM. All right, Reviewing additives. So when do we use additives? Additives can be classified as another polymer, or it can be classified as a small molecule that can be added to a formulation. So paint is an example of a formulation. Rubber is an example of a formulation. Even extruded plastic is actually a formulation that can contain processing aids or even viscosity modifiers or plasticizer. So any of these molecules or additives can be added to a polymer. In fact, it is big business. Many companies emphasize on using the right additive to get the desirable property. Take this example of these phthalates. Now, you've heard a lot of bad things about phthalates because some of them look at it as what we call endocrine disrupting chemicals. In fact, phthalates are still being used to process plastic. They are inexpensive. Some of them are being replaced. And if you wonder why you like a new car, the new car smells because of plasticizers like phthalates added into the plastic that was used to make the car part. Polymers have to be processed by heat, by curing, by forming, casting, extrusion, and so on. The melting point, the viscosity, the ability to form shapes after you have cooled are all very useful things because this is how you get packages, containers, plastic parts, car seats, etc. There are more types of processing, but just to give you an example, a polymer can be molded based on the melt or blown molded based on a film, compression molding, injection molding, reaction injection molding. In injection molding, usually a granular polymer or a pellet is melted and processed through a screw or extruder screw and then injected as a melt to a shape. This shape then assumes, the polymer then assumes the shape of the polymer, and once cooled down or quenched, you can remove this as a plastic part. How you make PET bottles. So PET bottles can be prepared by blow molding, or foams are generated with the use of physical or chemical blowing agents. Okay? Fibers can be prepared by extrusion through a spinneret and then quenching with water or air, and then finally winding. So this is basically the process that you form textile. Extrusion, as shown here, is very important because you can prepare different net shapes, sizes, or different geometries, pipes, objects, okay, can be formed by an extrusion machine. And we all hear a lot about 3D printing. In fact, 3D printing can be accessed through photopolymerization, viscous solution printing, or in general, as in most devices, by extrusion. It's essentially an extrusion of a filament or a pellet through a heated head coupled with a CNC machine or a machine or programmable machine that's capable of printing or extruding the material. Injection molding is big business, as you can see, using pellets or using polymers that are commodity polymers or additive ingredients are basically put on your hopper. The hopper then is introduced and melts the polymer pellets to give you a shape based on a mold. Okay. Another process is based on thermoforming. So in thermoforming, you can either do this by vacuum, mechanical, or pressure driven to take the shape or form on that plastic part. And many types of packaging materials are made this way. Here, just to review, for those of you, how can I name a polymer? It's very simple. You just take the name of a monomer, and then you add the prefix poly. So if your monomer is propylene, you add the prefix poly, it's polypropylene. Or if your monomer is styrene, you add the prefix poly, it's polystyrene. There is another way to name it. It's based on IUPAC rules, and that means you need to name the monomer using IUPAC rules and add the word poly. And this systematic nomenclature is good because it allows you to remove any ambiguity on the monomer structure and define some of its polymerizability. Now, other common polymers are shown here, okay? Polyvinyl acetate, polybutadiene, polyacrylonitrile, okay? Polyisobutylene, polyvinyl alcohol, okay? Without going through the actual uses of this of monomers, and these are very common polymers that are commodity produced. This is how they are named and the chemical structure. And of course, other names based on trade names, trivial names, or acronyms, like polyether ketone. Nylon is essentially made from polycaprolactam, polycaproamide, or based on amino acids, polyethylene oxide, PET, polyethylene terephthalate, and so on. Okay, and there are many other polymers that, of course, we don't have time to cover. Plastics is an industrial process. The volume is high. The properties are useful for everyday things. In fact, the big five in production is essentially polyethylene, polypropylene, PVC, and PS. And these polymers are made by free radical polymerization, coordination polymerization, and therefore, most of them are derived from petroleum-based products. Of course, we have other polymers or plastics that are of limited production, such as high-performance polymers like PEEK, PPS, PEI, or even nylon. They are usually important because they can do the job at higher temperatures or have higher impact strengths and so on. There's a lot of interest, of course, on recycling. So recycling means that you're able to biodegrade, or you're able to collect, you are able to purify and reuse. Okay, biodegradability means it comes from bio-based feedstocks. Again, for lack of time, is it possible to derive many monomers that are used for agriculture or agricultural waste that can be converted to polymers and eventually useful ingredients? So with the remaining time we have, I actually like to take some time now to introduce our group. So our group actually does a lot of polymer synthesis. This one related to the synthesis of what we call electro-optical polymers. So these polymers can be in the form of dendrimers, ladder polymers, different side groups that are electro-optically active. They emit light. They are used for photoconversion. They have hyperpolarizabilities or even nonlinear optical properties. So we've done that for many years, and we've reported them in literature, useful for devices such as solar cells, photovoltaic devices, and sensors. On the other hand, we have done a lot of work on what we call dendrimers. These dendrimers are synthesized by convergent or even divergent approaches. We can make dendrimers that act as ligands that are used to surround particles to produce what we call hybrid nanoparticle systems. We like to polymerize on surfaces, so we can graft polymers from, through, or onto surfaces using initiators or polymers that can be connected on surfaces. And this is very useful for modifying surface properties of objects, polymers, nanoparticles, and so on. Of recent interest to us are what we call nutty polymers. So these are templated polymers that we design based on the architecture of the initiator or macro initiator, such that we can force it to form catenated structures or even supramolecular nutty triple knots as shown here. And this requires careful planning and strategizing to form the macro initiator complex. Now, going towards some of our interests on processability, we have a big effort on 3D printing, taking advantage of the facilities here. So For example, we have the ThinkBox Institute that's present in our university, where we have access to a lot of 3D printing materials. I was also part of a um, center that was funded by the National Science Foundation that allowed us to extrude films of very high fidelity periodic structures such as these alternating layers, which we can then modify to produce interesting photonic band gap and particulate systems. And then lastly, we have a center called PetroCase that we use polymer science and engineering to solve some of the important problems and properties needed to advance the oil field chemistry and operation. And that can include propans, drilling fluids, and other types of assets used in the oil and gas industry. Skipping this part, we maintain a lab that's capable of doing synthesis, rheology, electro-optical measurements, coatings, morphology. In fact, a very important component in our lab is atomic force microscopy, where we do a lot of morphology analysis of different macromolecular architectures. And these are some of the techniques we have for characterizing oil field chemistry, including testing of properties under high pressure, temperature conditions. 3D printing. So we have a big effort in 3D printing. We like to 3D print different materials with at least 4 different types of methods. Viscous solution printing, FDM, SLA, SLS, okay? We like to take inspiration from nature or even use some of these materials for biocompatibility, okay? So, apologize for that slide. Some of the interesting materials we're using, especially for coatings for the oil and gas industry, includes the use of polybenzoxazine chemistry to make oil and water separators or superhydrophobic films. We like to use polymer to modify propans that are used for hydraulic fracturing. So resin-coated sands, different types of hydrogel or aerogel materials. We are interested in polymers capable of phase separation, complexation, formation of Janus nanoparticles, and different types of phase miscible or immiscible systems. Okay, and thus we try to make new polymer architectures based on hyperbranching, different types of black copolymer, graph copolymer systems, and so on. Some of our initial results enable us to use this for enhanced oil recovery or viscosity modifiers. And here, for example, is one system where we actually use grafting methods to modify graphene oxide and control its rheological properties tightly. So in this 45 minutes, I've taken a tour. You've taken a tour on an introduction to polymer science, engineering, short introduction of our group, and hopefully you find this tutorial useful and share it with your friends on a 1-hour vignette of polymer science. So with that, I'd like to thank you, and I'll be happy to answer any questions you may have.
All right, thank you very much, Professor Advincula. So now that we've reached the end of the talk on Polymers and Plastics 101 today, we are shortly going to transfer to the dedicated Q&A session. But a couple of housekeeping tidbits before we do that. First, if you are interested in more of Professor Advincula's work with his research group at the Department of Materials Chemistry and Engineering at Case Western Reserve University, you can visit his group's website, and I'll put it here in the chat, at rcapoly.net. If you are interested in any of the scanning probe microscopy solutions that are used by researchers for this particular application, you can also find out more about it from our website at parcafm.com. And we'd be more than happy to discuss what's available there on the cutting edge for your research needs. Lastly, just like I mentioned at the start of the hour, these videos, all these lectures are posted online. One of the repositories for these video recordings for all of our webinars, not just the ones that we do with Professor Advincula, are on the Park website as well under our Nano Academy section. And if you happen to have a YouTube account, and who doesn't these days, but you can subscribe to our channel on YouTube, and we also publish the videos there as well. So let's go ahead and turn things over to the queue of questions. If you happen to have any that come up, please send them in. Now is the time. Our only question right now in the queue, Professor, reads, is there a correlation of the molecular weight, let's say in kilodaltons, and size in nanometers of a particle?
Yeah, a particle can be in a solution, or it can be part of characterization by light scattering. So yes, depending on the particle, we can be dealing with the hydrodynamic volume of a polymer particle in solution, or we can be dealing with a solid state, or even a inorganic nanoparticle or hybrid nanoparticle. So usually with a higher hydrodynamic volume, it trends with molecular weight. So increasing molecular weight will give you a higher hydrodynamic volume. However, that holds true if you have a linear polymer. If you have hyperbranching or dendrimeric system, it does not hold linearly, or is actually governed by scaling parameters. On the other hand, a solid nanoparticle, which doesn't have a hydrodynamic volume but is a function of the diameter of the nanoparticle, is a straight linear relationship, and it can be an increasing molecular weight, but at the same time it behaves like a solid nanoparticle. Then it doesn't follow the hydrodynamic volume relationship with molecular weight.
Oh, actually, I had my microphone there muted for a bit.
Oh, okay.
I'm still here. So I know that obviously today's topic was on macromolecules, on polymers, and last year the right around this time the Nobel prizes were starting to be awarded, and last year we were looking into supramolecular chemistry and the development of nanomachines, and we actually did a webinar on that. And this week the Nobel Prizes for various fields have started going out, and it looks like this year the prize for chemistry went to developing cryo-electron microscopy for high-resolution determination of biomolecules in solution. I was wondering, Professor, do you have any thoughts about what that particular development was and what its significance is?
Yeah, last year it did. Is I would classify as a polymer-related Nobel Prize win. And in fact, personally, I know Professor Stoddart and Professor Sauvage, and that's very much related to the supramolecular chemistry that I defined as one of the things we're doing, and also during the tutorial lecture. So this year, the focus is on imaging, or the ability to investigate proteins, biomolecules that allow characterization. So unfortunately, I know I haven't had a chance to find things that might be related to polymer science for this year's award. But certainly it'd be interesting to see again how much polymer chemistry has impacted science and society in general, and who knows who will be the next year's polymer or Nobel Prize winner that has worked very much related to polymer science.
Very good. Very good. So with that, it looks like no more questions have appeared in the queue. So do you have any closing thoughts for next time, Professor?
Yes, I appreciate the audience. I appreciate the loyalty of those of you who have been following this series. I hope it has been useful to you as a review, or especially some of the more advanced state-of-the-art topics that we covered. And of course, I'd like to thank again Park AFM for hosting this webinar series. And I hope they have the opportunity to know more about their AFMs.
Excellent. With that, we are now going to close this session. But if you have any feedback for us, again, Professor Advincula can be reached at rca41@case.edu. I myself can be reached at gerald@parkafm.com. So if you have any comments or any suggestions for any topics that you'd like for us to cover in the future, either as part of the 101 series or maybe as part of a new series, please feel free to drop either or both of us a line, and we'll be happy to toss a couple of ideas back and forth. So until next time, we will have another webinar in the first week of Thursday from Professor Advincula, and Park Systems' own technical applications team will also have one, I believe, on the last week of November, right after we get back from Thanksgiving. Looks like our scheduled topics for next month are going to be on surfaces and interfacial phenomena. That's going to be our topic with Professor Advincula on Thursday, November 2. And we will also be doing a topic on ECAFM, which is electrochemical atomic force microscopy, with the Park staff as well next month. So keep an eye out on your email inboxes for those invites, and they'll be posted on the Park website shortly. Until then, on behalf of everyone here at Park Systems, as well as Professor Advincula, thank you very much for your attention, and we hope to see you again at a webinar in the future soon. Thank you, everyone, and take care.